Welcome to this video on 2D and 3D vector operations. To understand the concepts of this video, it will be important to know algebraic operations and vectors in 3D. Vector operations are very similar between 2-dimension and 3 dimensions. So if you have vector A with components ax, ay, and az, and vector B with components bx, by, and bz, then when we add the two vectors, the resultant x component is going to be ax plus bx, y component is ay plus by, and z component is az plus bz. When we subtract two vectors, x component is ax minus bx, ay minus by, and z component is az minus bz. Finally, if we were to multiply k by vector a, and k is a scalar value, then the x component, y, and z components are going to be multiplied by that scalar value. For example, let's take two vectors, vector A with components 0, -2, and 1, and vector B with components 2, -1, and -1. If we want to find 3 times A minus 2 times B, then we multiply the x, y, and z components of vector A by 3, and we subtract that from 2 times the x and y and z components of vector B. And when we do this, we get 0 minus 4, we get -6 plus 2, and 3 plus 2, and our final solution will be -4, -4, and 5 as the three components of the resultant vector. Let's talk about a few properties of vectors, and this applies to all vectors. Vector A plus vector B is equal to vector B plus A. This is called a commutative property. If you were to add vectors A and B together in brackets and add that to C, that's same as adding A to B and C in brackets, and this is called the associative property. If we were to add vector A to a 0 vector, then that's same as 0 vector plus A, and that's vector A. That's the additive property. If we have vector A plus -A, that's same as -A plus vector A, which is a 0 vector, and this is called the additive inverse property. If you were to add vector A plus B and multiply that by a constant value k, that's same as k times vector A plus k times vector B, and this is similar to the distributive property. There's another very useful property. So if you wanted to take the size of k being a constant value multiplied by a vector, that would equal to the size of k, or the absolute value of k, multiplied by the size of vector A. Okay, another very useful property can be achieved because we can add and subtract components of different vectors. So if we have vector A plus vector B is equal to vector C, if we want to isolate for vector A, then we can just subtract vector B from both sides, so we get vector C minus vector B, and if we want to get vector B, we will subtract vector A from both sides, achieving vector B is equal to vector C minus A. Similarly, if we have some vector B is equal to vector A multiplied by some constant value k, then to isolate for vector A, we can divide both sides by k, giving us vector A is equal to 1 over k multiplied by vector B, or just vector B over k. A quick example of this would be if we had vector B, which is equal to 3 times vector A, and if vector B was equal to 2, -1, 3 as its components, then vector A would be 1/3 of vector B, dividing both sides by 3, and that means that we will simply multiply 1 over 3 by all the components of B, getting 2 over 3, -1 over 3, and 1 as our final answers. Okay, here's a summary of everything we talked about during this lesson, and you can pause the video and copy it down if you would like to. Now we are going to look at a couple of examples. In the first example, we have a line segment with points A, B, C, D, and E, and points A and B are given, and the distance between all the points are the same. We want to determine the coordinates of point E and the magnitude of AB multiplied by vector AE. To approach this question, we have to kind of look at what we have. We have vector AB because we can calculate it, and we know that if we multiply that by 4, we will get vector AE because the distance is the same and they're in the same direction. So vector AB can be calculated by taking the coordinates of point B and subtracting them by coordinates of point A. So by doing that, we will end up getting x component of 5, y component of 1, and z component of -6. We know that AE equals to 4 times vector AB, so we multiply all the components by 4, getting 24 and -24 as our 3 components. We know that vector AE is equal to the x, y, and z components of point E minus the x, y, and z components of point A. We have everything in point A, and we know what AE is. So we're going to equate these, and we're going to make 3 equations out of this. The first one is the x component of E minus -1 is equal to 20, y component of E minus 2 is equal to 4, and z component of E is equal to -3 is equal to -24. We will then solve for all the components. We will get the x component of E equals to 19, the y component is equal to 6, and the z component is equal to -21, and we can write our final answer as a point with its proper coordinates. For part B of the question, we need magnitude of AB, so we already have vector AB, so the magnitude is equal to its x component squared plus y component squared plus the z component squared, and that will give us 5 squared plus 1 squared plus -6 squared, which ends up being square root of 62. We now need to multiply this by vector AE, so root 62 multiplied by all the components of vector AE, which we already have also. So that will give us root 62 times 20, 4 times root 62, and -24 times root 62 as our final answer. For the next question, we want to determine the values of x and y given that x multiplied by a vector 1, -2, 0 plus y times vector -3, 2, 0 is equal to a vector -2, 4, and 0. We can make this into 3 different equations for different components of the vectors. So for the first one, we got x times 1 plus y times -3 is equal to -2. And for the y component, we got x times -2 plus y times 2 is equal to -4. We can rewrite this. So first one is x minus 3y is equal to -2, and -2x plus 2y is equal to -4. We got equations 1 and 2. We multiply equation 1 by 2 in order to be able to eliminate the 2x. And we add the 2, and we end up getting that 0 minus 4y is equal to -8. We divide both sides by -4 to get a y value of +2. Now that we have the y component, we sub the y is equal to 2 into either equation 1 or 2. So in this case, equation 1, x minus 3 times 2 is equal to -2. And we solve for x, and we get x is equal to 4 as our final answer. We can check this for the z components. In this case, 4, which is our x value, multiplied by 0 plus 2, which is our y value, times 0 equals 0. And that makes sense. I have prepared a few practice questions for you folks to try out, and I will try to post the solution to these problems as soon as I can. I hope that this video has helped you a little bit with understanding vector operations, and thank you for watching.